Welcome to PV 911, First Responders and PV Systems. This video is to show you how to work safely in the presence of a live solar-sourced electrical generator, in other words, a PV system. Let me first introduce myself. I'm Kelly Province, CEO of SolarGen. We founded the company in 2002 and started doing training in 2007. I'm IREX certified as a master trainer, NAPSIP certified as a PV installation professional, and a licensed master electrician. A few terms that we should be familiar with before we start. Photovoltaic, represented as PV, also known as solar electric. This is the conversion of photon energy into electron energy, so that's light to electricity. An inverter is a device that converts DC electricity into AC electricity. So we take the PV array energy, which is DC, and convert it into AC with the inverter. We have several different types of inverters. The interactive inverter is one that operates in parallel with the utility, so it pushes power into the utility. Whenever the utility power shuts down, it shuts down with it. A standalone inverter is designed to operate off-grid, separate from the utility. It develops its own waveform and uses the battery bank as its storage and power source. A multimodal inverter is one that can operate either way. So it's basically a standalone inverter that has interactive inverter capabilities. National Electrical Code. This is the guideline that we follow with all electrical installations. In Georgia, we're following the 2014 edition of the NEC. And it is now in effect and law for the state and most of the United States. One term of particular interest to first responders is readily accessible. What you want to be able to do is come up to a house, disconnect power as quickly as you can, or a structure. And readily accessible doesn't necessarily mean that it's on the outside. It could be inside of the structure as it is interpreted from the National Electrical Code. So I want to make that clear as we start to go through this presentation material. So how does this system work? How does PV work? Well, we look at the solar source, of course, as our sun, and the energy leaves the sun and reaches Earth about 8 minutes later. We actually have enough energy from reaching the Earth from the sun to power all of the Earth's electrical needs, all the power needs, plus quite a margin beyond that. However, it's very difficult to take solar energy and distribute it around the Earth, and we have to also figure out a way to store the energy so we can use it at night. Upon striking the surface of a PV cell, photon energy is converted to electron energy. A fraction of a second later, it reaches an electrical appliance. The conversion process, band gap magnetic field conversion, is what we have with PV cells, is only about 16 to 21% efficient, depending on the technology. We consider 30% to be the maximum that we'll reach for this process. What's happening within the cell is the electrons are excited by the photon energy and they start moving. In order to rack these off, we have to have conductors embedded into the surface of the PV cell, and we have to connect a wire or some type of conductor from the negative to the positive. If we have an appliance or a battery or something that uses the energy in this circuit, it will use those electrons and convert it into another type of energy. And then the rest of the circuit completes back to the positive side of the cell empty, and then it refills and keeps going. So this is basically the process of the photoelectric circuit. PV cells are manufactured from a number of different materials and in different processes. One material that's used is silicon. The silicon is purified and then melted and then regrown as a crystal. The crystal is very pure, so we have very consistent performance from it. We cut this crystal into wafers, about 180 microns thick or thinner, and then we dope one side with a positive and one side with a negative material so that we create a magnetic field. And now that with a magnetic field, we can create an energy flow circuit. We also cover the surface that faces the sun, with an anti-reflective coating. That's that blue color that you see. And then we embed contacts into the surface so that the electrons, when they're excited, move to a conductor and move through the circuit. PV modules are comprised of multiple PV cells. These cells are usually connected in series, positive to negative, until we reach a voltage that is in the operational range that we want to use. Now each cell's voltage is approximately a half a volt. So if I take 60 cells, connect them all in series, I end up with somewhere around 30 volts. The other component is amperage. So each cell, depending on its size and the intensity of light, will produce, somewhere between 1 amp up to maybe 10 amps. These are tested, standard test condition, with a radiance that's consistent and a temperature that's consistent. So when it varies from those temperatures or radiance, it is different. So what you're seeing here, the 31.6 and the 8.7 amps, is based on a controlled light intensity and a temperature. And it's also dependent on the actual size of the PV cell. So we have 6-inch cells, we have 5-inch cells, and we have other different dimensions as well. So the amperage will depend on that actual dimension. The wattage of the PV module is, of course, the product of volts times amps. PV arrays are comprised of multiple modules. These modules are installed parallel to the roof, about 5 to 6 inches above the roof area, on rails and flash penetrations that mount directly to the roof. About 99% of the residential rooftop installations are designed something like this. An alternative method of installing PV modules on a roof requires an alternative manufacturing process for the PV modules. This is a thin film application. The ones we're looking at here are actually amorphous silicon, non-crystalline, but now they're making them out of another material called SIGs. A shortened name for it is SIGs. It's basically a thin film application that's applied over stainless steel with a high temperature polymer coating on it, and there's an adhesive on the back side so it sticks to the metal roof. You won't see very many of these, but there are some in the state of Georgia. 2003 to 2011 is when this was primarily done in the state. There are some products coming on the market now, but like I said before, the likelihood of seeing this is pretty low. Another module type and installation method would be to have a solar shingle. This PV shingle looks like a standard shingle and it functions as a shingle does. We don't see very many of these in the state of Georgia. As you can see from this map, the products that are coming onto the market right now are available only in those orange states. You may see these in the future. The likelihood of seeing one now is pretty slim. On commercial flat roofs, we usually see either ballasted, the lower right picture, or direct mounted on the left. The left is the most secure method of attaching to the roof. However, it is a little more expensive than the one on the right, so the one on the right is the most common. They use ballasted concrete blocks to offset the wind lift. It's very successful. There have been some incidents where the wind flipped these over, so there is a potential for that. Low-sloped commercial roofs are typically installed similar to a residential system. The one on the left is installed parallel to the roof and attached directly to the roof. The ones on the right have a little bit of a tilt to them, so sometimes you see that with these metal roof installations. Commercial ground-mounted systems typically are more utility scale than they are commercial, but occasionally you'll see a ground-mounted system. In this case, all of the DC, everything's off of the roof, so there's not much of a concern. It's contained within itself, separate from the building. Single pole mounts are common with commercial and residential installations. This type of mount is away from the structure, so it really doesn't pose any kind of a hazard for a first responder. Parking canopies or canopies next to the roof are very common these days. So you may see a canopy that's actually attached to a structure, or you may see the canopy that's separate. If it's separate, it really poses no hazard. All the DC and AC are separate from the building. If it's attached to the building, then treat it as if it were on the building itself. For steep sloped and low sloped roofs, residential and commercial, we should see a margin from the edge of the roof of 3 feet. It doesn't have to be on both sides, but it would be ideal if it were. And also between two roof sections in the valley. Also from the peak of the roof down to the edge of the roof, 3 feet is the suggested margin as well. As you can see with these examples, 3-foot margin is maintained all the way around the roof. The one on the upper left is an exception where you have the 3-foot margin to the right and the top, but the left-hand margin does not have that. You will see exceptions to this. You'll see where people have covered most of the roof. It may make it very difficult to access the roof, so this is recommended. It is not law in any state that I know of except for California. The gross majority of flat commercial roofs do not have this kind of concentration of PV installation. Most of them have much greater margins than what you're seeing here. These are minimals. 6 foot to the edge is the minimal, and 4-foot walkways into equipment, 6-foot walkways that are major between the areas, and no more than 150 feet between a walkway. But generally speaking, what I've been seeing in the field is much more access than this. Well, let's talk about system types. We have utility interactive systems. This is a grid tied or on grid. They use these different terms for it. They produce power in parallel with the utility power. When the power goes off from the utility, so does this PV system. It shuts down. There is no AC power produced when the utility goes down. A standalone off-grid system is different. It is internally fed from a battery bank, so whether it's connected as a bimodal, which would have a battery bank and be connected to the grid possibly, or if it's a standalone, there is the potential of this energy being present whenever the utility power is off. Bimodal systems, we refer to these as utility interactive, where they actually can sell back to the utility. When the power goes off, it becomes a standalone system. We're starting to see net zero or self-consumption systems as well, where they have a battery system and they're trying to stay off-grid and not buy power from the grid and produce all their energy feeding into a battery system. So it's similar to utility interactive in that it's using the utility power, but it's not selling back into the utility. And then we have the standalone, which simply uses the utility as a backup. Let's take a look at utility interactive inverter systems. We're going to look at the operation of the system, how it operates, safety features, look at the voltage exposure from different types of systems, and what types of utility interactive inverters are there. Also, what are the utility and NEC requirements for labeling these PV systems? This is a classic interactive inverter system setup. You have the PV array, you have the inverter, you have a disconnect from the PV array to the inverter, and you have an AC disconnect from the inverter to the main panel. In this case, we're using a string inverter for the example, so the inverter is located either inside the house or on the outside of the house. If this system had microinverters, the microinverters would be located up underneath the PV array, and they act as the DC disconnect themselves. So there's not a DC disconnect with microinverters. So with this system, this DC disconnect would probably be located either inside the house or on the outside of the house. Either one is readily accessible. The AC disconnect may be right next to the inverter, and it may be outside or inside. If it's outside, it's probably the only AC disconnect that they're going to have, because it'll be one and the same with that utility AC disconnect that you see on the left. If it's inside the house, then there will be an additional AC disconnect as the utility requires this in order to connect to the utility system. The power then feeds back into the main panel and then feeds into the house and of course out to the meter if it's selling power outward. The flow of energy from the PV array through the inverter into the AC circuitry in the house can be two directional. Once it reaches that main panel, the electrical box, it depends on whether the house is using more energy than what the PV system is using or less. If the house is using more, then there's power coming from the grid and from the PV system inverter. If the house is using less, let's say everything turned off in the middle of the day and the PV system's producing a lot of power, it'll be flowing out to the utility. If there's a utility outage, this will be severed in the inverter and no power will flow out at all. So it's a safe system AC wise as soon as the power is lost. What are the safety features that are built into utility interactive inverters? The IEEE 1547 standard now requires that we have ground fault, arc fault, and anti-islanding. Ground fault sensing and disconnection, this is whenever we have an internal breach between the PV cell, the parts of the PV cell, the negative and positive, to the frame or to another grounding material or a conductive material, which could cause a fire. An arc fault is where we have a poor connection. We could have a rodent that is chewed through a wire or something, and the system's still operating and trying to produce energy, so it's arcing. So we want the inverter to shut down. So the arc fault protection device and the ground fault protection device shut down the inverter in case of these two events. The anti-islanding is where if the utility power is lost, the inverter stops producing power. This is to protect linemen, anyone that might be in the vicinity of a down power line. So this makes it safe on the AC side, and all inverters are pretty, interactive inverters are pretty safe on the AC side. The DC side is a different matter. We still have potential on the DC side, on all PV modules and all PV systems. With the older types of systems for residential, we had higher voltage type conversions. We had string inverters, and this high voltage is very hot. It's 10 times hotter than AC. It's only about 1/10 as likely to cause fibrillation in the heart, but it's still dangerous as a shock hazard. So we consider anything below 80 volts to be fairly safe against arcs, and anything below 30 volts to be absolutely safe against any kind of a electrical shock. I've touched 50 volt systems on battery banks and have not been shocked, so I really think that 50 volts is the safe zone, but for the sake of extreme caution, the NEC states that 30 volts or less is considered safe. Okay, so what is our voltage exposure during a shutdown? We know that the AC power shuts down. All we have to do is pull the meter or whatever. It will stop the AC from producing. DC power is still present, so what are we looking at? Residential inverters, the interactive inverters, let's do a little history. 2009 and earlier, everything was a string inverter. They operated somewhere between 150 volts to 500 volts. Now we're talking about interactive systems here. That's a pretty high voltage. That has the potential to electrocute, has potential to create a fire. So that's 2009 and earlier. 2009 to 2013, microinverters came into the market, and they're so friendly and easy to use that installers jumped on them automatically. They weren't even thinking about the safety features of this microinverter. It was just an easier way to install a PV system. So they're very friendly to the installer, and that's a good thing for first responders because the voltage is only 22 to 48 volts, which is in the safe voltage range. 2014 to present, well, now we have not only the microinverters, but we have another product, SolarEdge. This is an individual manufacturer, has a PV optimized controller attached to a module. So it's not a microinverter, but it has the safety features of a microinverter, and it drops the voltage down to 1 volt during a power outage. So anything after 2014 is probably, if it's an interactive system, is probably one of these two. So you have a good safe situation. All of the voltage is reduced down to the module at a low level. On commercial interactive inverters, it's a little bit different. We do have some microinverters on commercial systems, but they're more expensive and so they're not hitting that market quite as strong. 2012 and earlier, most were high voltage, 250 volts up to 600 volts. 2012 to present, we still have the high voltage. However, we have inverters that are actually located, even though it's a high voltage string inverter, they're located where the PV array is. So we're not looking at conduits running all the way down to the ground like we did before 2012, which was typical. We're seeing these inverters being mounted where the PV array. So we have a little more safety in the commercial system in that it's contained to the PV array location. Let's look at the three different types of utility interactive inverters that we'll typically see on our residential install or commercial install. The microinverter, which is matched 1-to-1 to a module, so the individual module DC voltage will never be more than 22 to 48 volts, so it's a safe voltage. And when the utility shuts down, the AC shuts down and shuts down all production. So that's a safe installation. String inverters, it depends on what type of string inverter it is, but the typical residential string inverter can be anywhere from 150 to 600 volts. These are the older models. The newer models, the Solar Edge with PV optimized strings, drop down to 1 volt with a power outage. So they're just as safe as microinverters. Commercial string inverters, they actually, I think we have string inverters up to 50 kW now. It's a very large inverter, but it's mounted at the location of the PV array, which makes it inherently safer because we're not running DC conductors through conduits in other parts of the building, so you can safely go through the building and do what needs to be done and stay away from the PV array itself and be relatively safe. We do have a 1,000 volt consideration now for commercial PV systems. This is on the DC side. We're not looking at the AC side on that, but 1,000 volts DC is a greater arc potential, so we do need to be aware of that. String inverters with optimizers are starting to show up in commercial as well, but they don't dominate the commercial market. So with a microinverter, basically they have an AC circuit that loops from one microinverter to the next, and they may have 15 to 21 of these inverters with their accompanying modules in a single circuit that back feeds into a main panel. There's disconnects up there underneath the modules for the DC and for the AC, but those are not readily accessible disconnects. You don't want to try to get into that. If you want to shut the power down, there's two ways to do it. You can pull the meter, or you can disconnect the main inverter AC disconnect, which is shown here in this picture. It states that it's a photovoltaic AC disconnect that's required by the NEC and by the utility. It'll also state what the operating voltage is and the operating amperage. And it may state down below that it complies with the 2014 rapid shutdown requirement. Now that may or may not be there on a microinverter. But if you see an AC disconnect, you're looking for the type of system that is operating there. You want to see if it's a Solar Edge PV optimized or if it's microinverters. If you see that, you know for a fact that it's safe all the way down to the module. If you don't, you don't know for a fact that the DC circuit is safe. So look for that first. Here we have the standard installation of a microinverter and the rapid shutdown. What we have is PV modules on this roof with microinverters behind them. We have a combiner box up on the roof that feeds down to the AC disconnect. Disconnecting this or pulling the meter shuts down everything to the module level up here. Here we have a string inverter, a residential string inverter. You can turn this AC disconnect off or pull this meter and it will shut down the AC power. But if it doesn't have optimized, voltage safe optimizers on these PV modules, then you have high voltage DC running from the PV array down to the inverter. So be aware of this conduit. There is high voltage DC in it, unless it's marked otherwise. I've mentioned the name SolarEdge a few times. They are the only inverter that is matched to their PV optimizers. They're not the only company that manufactures PV optimizers. They're getting more and more popular and more common. And here they have the optimizers mounted behind where the modules are actually going to go in place. So if you see the SolarEdge, just disconnecting the AC will turn this off automatically. So look for the SolarEdge. And as we move into the industry as it develops, you'll see more of these optimizers competing with these guys. And you should see that indicated on the DC disconnect that it does have an optimized rapid shutdown system. So if you see a DC and an AC disconnect and an inverter in between them, you know that it's a string inverter. Could be that this string inverter is on the inside of the structure, and it could be that the DC disconnect is inside the structure too. But if you see on that number 5 the AC over there and it says a rapid shutdown system in place, then you're safe. The rapid shutdown requires that within 10 feet on the outside there has to be a disconnect, so you know that there's no conduit running in other parts of the structure hiding this high voltage DC. If this conduit does not come from the roof straight down to a disconnect and it actually goes inside the structure, it's required that a remotely activated disconnect be placed within 4 feet of the entry point into the roof. Now that's 2014. That was not enforced until 2015, and a lot of these products, rapid shutdown systems, just now are on the market. So basically what you're looking for is either that it's microinverters or that it's a SolarEdge with PV optimized. Otherwise, there is high voltage from that disconnect point up to the PV array. So just find out where it's going, and that's your danger point. Early commercial systems had what they call central inverters located usually on the ground floor, either inside the building or outside the building. If it's on the outside of the building, you can at least turn the system off and isolate the DC at that point, and you can see the conduit, which is usually running down the outside of the building, so you stay away from that. That's where the high voltage DC is. On newer systems and some of the older systems, the inverters are located proximate to the PV array. Now it's very common. The most common way to install these systems is with the inverter, whether it's a microinverter or a string inverter, right next to the PV array on the roof of the building. Older systems may have had these string inverters inside. So this is showing it inside of a parking area. So hopefully there would be a plaque somewhere indicating where this is run to. Let's review the commercial voltage considerations. Microinverters, we know that it's isolated, to the module. The string inverter is usually located close to where the PV array is. Not necessarily, but usually it is. So if you can observe that, you see the inverters located close to the PV array, then all the DC is isolated at that point. If you see a ground-mounted inverter, then you know that there's DC feeding down to it. So a big central inverter, of course, means that there's very high voltage, high current coming through those conduits. So try to avoid those if you can in any way. Both the utility and the NEC have requirements for labeling PV systems. The National Electrical Code is enforced by local jurisdiction, which may or may not know what to look for. The utility knows that they want a label and a disconnect, so they're going to be the final line. So let's take a look at the requirements from these two entities. The NEC requires that the DC disconnect be labeled as shown in this picture, and also labeling the operating voltage and max voltage and current. And it also requires that we have some type of a labeling on the source conductors. So if we have conduits running to the inverter from the PV array, they have to be identified some way like this, very brightly, with the photovoltaic power source. This has only been in the last few years of enforcement, so anything installed prior to that probably does not have this label on it. They all have the DC disconnect, but readily accessible, as we said before, can be on the interior of the structure. So this may not be where you can actually get to it readily. The 2014 NEC had a new requirement for rapid shutdown of PV source circuits. This is a great requirement, should have been out a long time ago, and basically it says that if you have DC, high voltage DC coming off the PV array 10 feet away from the PV array on the outside of the building, or 5 feet going into the building, that you have to have a remotely activated disconnect. So this is basically this little mechanism here, which you push that button and it would, in a box, a remotely activated disconnect box, would shut down the PV system or drop it down to no more than 30 volts within these two distance parameters, outside or inside. And there should be a label that states, PV system, rapid shutdown system in place. So you may not see this. This is a new requirement, so you may not run into this for a little while, but you should start seeing this on all new systems if you happen to be out on one of them. The NEC also requires that an AC disconnect labeled and placed in a readily accessible location be on site. Now, it does state that if it's not outside by the meter, that there has to be a plaque out there. But the utility is also stepping in on this one. They require that there's an AC disconnect that's labeled as well, so usually this is one and the same. So if you don't see it next to the meter, there should be a plaque right next to it describing where it's located. And the utility company doesn't allow this to be inside of these structures, so you should see one of these AC disconnects outside of a structure on all installations. Commercial, they're allowed to have it in a locked electrical room, so that's an exception. The NEC requires this plaque, of course, if the disconnect is not located next to the utility meter. And of course, this would probably be the same disconnect that the utility would require. So it'll either be a plaque that clearly states where it's located, or it would be a directory showing a map to it. So there's no standard on this, so you may see a variety of different labels trying to indicate where this is. Now let's take a look at standalone and multimodal inverter systems. These are not the dominant systems installed. Most of the systems you'll run into, if you run into one, will be an interactive system, but they're out there and they're going to become more common. The good thing is the ones that are being installed in the future have more labeling, are safer, so they function in a friendlier way to first responders. The older systems, not so much. So I want to go over all these aspects of standalone and multimodal inverter systems and what you should be looking for out there. Here's the linear flow of a standard standalone PV system. So this would be an off-grid system with no utility anywhere near it. It could also be grid connected, but actually a standalone, just using the grid as a backup, as a generator. So instead of the generator, it'd have a utility connection. So this happens occasionally. It's not predominant. So what you're seeing is a charge controller that actually takes and manages the PV energy into the battery bank. These battery banks are probably located in the basement of the garage, and the inverter, the battery-based inverter, would be located at the same location. If there's a generator, it's located, of course, outside. The DC distribution center, this may or may not be in one of these systems. Some of these customers have DC loads, most of them do not. So more than likely what you're going to have is the AC distribution center. You'll have one AC panel located in a typical place inside the house, and you should have an AC disconnect located outside or a plaque indicating where it is. Since this is not a grid connected system, if it's standalone, the utility's not going to have any enforcement to say, hey, you need to pull that AC disconnect outside. It's up to the local authority having jurisdiction, and they may not have any idea where that AC disconnect should be on the outside. So there may not be a plaque, and there may not be an AC disconnect, although it's required. So if you saw a PV system and you don't see an AC disconnect on the outside, you've got a problem. You're looking at the garage possibly, or the basement, if you can get to it to turn these systems off. With a bimodal system, you may have an interactive bimodal system where this inverter, same as the standalone inverter, but would operate to sell excess power back to the utility. Then again, it may be a non-cell type of multimodal inverter, whereas it can operate off-grid in a lot of different modes. So in that case, it becomes a standalone system, and you wouldn't see the AC disconnect. It's supposed to be outside, but like I said, there's no utility to force that unless they're selling power back to the utility. So in either situation, what you have is the possibility of a PV system feeding into a battery, into an AC panel with no exterior access. It's required to be there, but if the enforcement's not in place, then it could be that the AC disconnect is interior. So let's look at these safety features that are built into these battery-based systems. Standalone inverter, there's no fault sensing or anti-islanding feature, so of course there isn't an anti-islanding feature because it's not connected to the grid, but the fault sensing is actually in the equipment such as the charge controller or in a DC panel, so the inverter doesn't do this. With a multimodal inverter, if it's in cell mode, then it would have the anti-islanding feature, of course, so that would shut down. So the charge controller or the DC panel is where your fault sensing, your ground fault, and your arc fault would be. So they'll do the job that the interactive inverter was doing with the interactive in systems. How about safe voltage on the battery system? Well, with residential systems, unless it's a completely enclosed battery system such as the Tesla Powerwall, which is not available yet, it's going to be a 50 volt system. So 50 volts is pretty safe. I've touched the terminals of the positive and negative and felt nothing, so that doesn't mean it's not potentially hazardous, because it is over 30 volts, but it's not inherently dangerous. Now the DC coming from the charge controller is a different story. These usually operate no more than 150 volts, but that is enough voltage to create a shock and possibly a fire. So you have hopefully metal conduit all the way to the DC system. It's required by the code, and hopefully they followed the code. But you would have to look from the PV array location to the battery-based location. If the PV array is on the ground, not a problem. There's going to be a DC disconnect either at the PV array or on the structure. So you can disconnect that and shut down the DC from coming in to the PV system. But the battery bank will still be there, and it'll still be operating at that voltage. So hopefully it's contained well enough that you don't have to do anything with it. So the standalone and the multimodal system operation, if the AC is disconnected on a multimodal system, this part of the system is still operating. So here's the backup loads in a multimodal system. It's always feeding power to this panel, and unless you can get to that AC disconnect, the AC power as well as the DC power are present in this PV system. So if you see that it's an interactive system, when you come up to the structure, then you isolate that it's either microinverters or a string inverter with a PV optimizer on it or not. If you don't see any of that, then you start thinking, is there a battery system? And you look for a plaque that indicates that there is a battery system in place. And if you don't see that, there's still the possibility that there is one. Just because it hasn't stated that there is doesn't mean that there isn't one. Here's a couple of examples of battery systems. Typically the battery systems are installed in one of two types of boxes. Either a wooden box that has an anti-corrosive paint or coating inside of it, or preferably a metal box, which of course is fireproof and anti-corrosive. But I've seen a lot of battery systems that simply set on the concrete floor, on a pad, but they're set open without any cover on them because they're sealed batteries. If they're sealed batteries, they don't lose any gases to the atmosphere, and technically, as long as the room has a little bit of ventilation in it, they could be open. What's the big hazard? Well, the batteries, if they're flooded, if you were to spray enough water on them to cover the terminals, which are usually 12 inches above, then you could have a shorting and they could melt down and cause a fire. Lead acid batteries are not very prone to do that. They don't discharge current that quickly. Lithium ion batteries are a different story. And of course lithium ion batteries are expensive and they're just now really hitting the market, so I think they will be covered by a lot of safety features. So what we're looking at is lead acid batteries, typically in enclosures. If not, you have to get the water level above the terminals. Terminals are usually protected. If you had falling debris, metal debris falling on top of it, you could get a short on it, so there's potential for that. But generally they're isolated safe. The disconnect, to disconnect the DC from the battery is usually up by the inverter. In this case it's down on the structure itself. These are disconnects on the battery structure. AC disconnect is in one of the panels next to it, and here it's in this panel and in this panel on this particular system. So garage or basement is the most likely place that you're going to see these battery systems. So let's review the safety concerns working around a battery-based system. PV array voltage pre-2014, most of them are going to operate somewhere between 60 to 120 volts. There's a few charge controllers out there that operate up to about 500 volts. They don't dominate the market, but they are there. So there is a possibility that high voltage DC coming in all the way to the garage or to the basement. Post 2015, all systems must have rapid shutdown that drops it down to 30 volts. So 2015 going forward, we have a lot of safety measures in place. It's prior to that we have a little concern. PV array disconnect protection. It may be outside, it may be inside. If it's a ground mounted system, it's probably outside. If it's a roof mounted system, then you hope that it's outside. That makes your job a lot easier if you can trace that that conduit. If it's located inside, then you're going to have to look either at the basement or in the garage where it's probably located. And as I stated before, the battery bank safety and disconnect. The disconnect is located near the battery. The new code requires it to be within 5 feet of the battery bank. But before it was probably no more than 12, within the same room. So it's in the same room as the battery bank. And the terminals are usually high enough above the floor that there's not a shorting issue from water, coming into it from trying to put out a fire. But if debris fell on exposed terminals, there could be a shorting. So there's a slight possibility there. The NEC requires for standalone systems on structures that there be these two labels, or at least one of them. The label on the right is required, period. This structure contains a standalone electrical power system. The one on the left is only required if there's not an AC disconnect out there that's obvious. So when you approach a structure, you either see the label stating and telling you where this AC disconnect is, or you see the AC disconnect, one of the two. So I think most off-grid systems will comply with this. Some little backwood cabin may not, but if it's a home that's off-grid, I think you'll probably see this most of the time. Where you won't see this, possibly, and where you should see this, is if it's a multimodal system. So it's connected to the grid, but it also has a battery system so that when the power goes off, it becomes a standalone system. Because of the fact that it can be a standalone system, it has to comply with the standalone labeling requirement. However, some people don't interpret that clearly, and so these may be missing. If you approach the structure and you see that there's a PV array on the roof and there are AC disconnects outside and labels, then you're probably okay and follow whatever instructions as far as location is on the labels. If there aren't any labels on this house and it's grid connected and there's no disconnects outside, then there's probably a battery system somewhere in that house or structure. More likely, if there's a violation of this, it's probably going to be in a house as opposed to commercial. So anyway, I don't think the probability of running into that's very high, but there is a possibility of it. So as with the interactive system, there should be an AC disconnect outside of the premises or inside the premises with a label, indicating where it is. Now, if this is an interactive bimodal system, there will be at least one disconnect outside for the utility to use to disconnect because they don't trust the anti-idling feature in the inverter. But the other AC disconnect for that backup panel may or may not be outside. It should be, and it should be labeled the same way as this is. Well, let's review what we've been looking at and look at proceeding safely on or into a structure with a PV system. Safe voltages with PV systems. 30 volts or less we know is safe. We're not going to get any kind of an arc or any kind of a fibrillation out of a 30 volt PV system, so they're considered safe. Low voltage, less than 80 volts, is unlikely to cause an arc. Now, it possibly could create a shock for a person, so there is a danger there, but the possibility of an arc that would cause a fire under 80 volts is very unlikely. Voltages over 80 volts is where we get into an issue not only with the possibility of shock, but also with fire. So this is kind of a gauge for which voltages are dangerous in which situations. First actions when approaching a site with a PV system in place. Daytime conditions. Observe the location of the PV array. Ground mounts will have DC disconnects at the array or on the house. I doubt if there's any PV systems that actually have the DC disconnect in the house if the PV array is outside. A roof mount may have one of three disconnects. AC disconnect for microinverters, DC disconnect for older string inverters, rapid shutdown disconnect for new string inverters. So these are the disconnects that you would see for a roof mount system. Consider the need to shut down the AC power. This will shut down the interactive inverter, so all AC power is down and there's no conversion going on. There's only potential energy at this point. Observe the conduits that lead from the PV array to the house and outside the house. So if the conduits are running outside, it's very easy to observe. If they're running inside the house, it's a little more difficult to observe unless you know where they're going. And if you don't know where the inverter is located, then that's a bit of a mystery. So AC or DC disconnect indicates that microinverters or a rapid shutdown system, and so there's really no more concern for the conduit. If there's no microinverter or rapid shutdown indicated, avoid damaging the conduit. Try to stay away from it if you can identify its route. Observe plaques indicating energy storage system on site. So that's the next thing you look for. Is there an energy storage system? And if they have a plaque, then all you have to do is pay attention to where it is indicated that the system is located, and that'll kind of put you in a safe zone as far as where there is potential. Nighttime conditions seem to be safe since there's no PV system working, there's no DC potential outside. However, there is the possibility that there could be an energy storage system on site. So look for the plaques to see if there's an energy storage system. If you don't see any AC or DC disconnects outside, but you do see a PV system, pretty good indication that there's an energy storage system, because the utility would require an AC disconnect outside, and if there's not one, then they don't know about the system, and more than likely it's an energy storage system that's sort of in violation of all these code requirements. So daytime system, you have a lot of potential. Nighttime system, really the only potential is if they have an energy storage system. Next few slides we're going to look at have some drawings that make it a little easier to see what we've been talking about on the previous slides. In this drawing we have a roof-mounted array with a disconnect near the meter. So you approach the structure, even if you don't see the PV array on the house, if it's on the back side, you would see that there's a DC and an AC disconnect and an inverter out there. So it would be very easy to tell that this needs to be shut down. So you can shut down 1 and 2, that stops all the AC power and the DC at that point. However, the potential still does exist from the PV array to number 1 where that disconnect is. This being the case, you want to be mindful of that pathway. Where do you think that conduit may run? If it's on top of the structure, on the roof, it's easy to see. If it's not, you just have to imagine where it possibly runs to get from one point to the other point. Here we have a roof-mounted array with a disconnect away from the meter. So we have the meter on one side of the house and the AC disconnect, where number 2 there is located, on the outside of the house, the opposite side. So we should have a plaque over by the meter. There should be a plaque indicating where that AC disconnect is, number 2. The DC disconnect may be on the outside of the house, but more than likely they took a straight shot and went to where the inverter was and put the DC disconnect there, because it only has to be readily accessible to meet the NEC code requirement. So the DC disconnect and the inverter will have to be spotted. If there's not a plaque, if they didn't provide additional information telling you where the inverter is, then you'll have to look for it. So in this case, with an older string inverter system with high voltage, you can shut down the AC, but the DC potential is still in there. It's in a conduit, but there is still potential inside the house from the PV array to wherever that disconnect is. So finding that disconnect would be possibly the next important thing to do. Now in this drawing we see what is more typical these days is microinverters. So with a microinverter you have no DC disconnect. Location number 1 is the DC. There's no load rated disconnects in this system. There's just microinverters up there, and at number 2 you have the AC disconnect. So this system is safe whether you pull the meter or whether you throw the disconnect at number 2. And this is the PV system that you really want to see if you're approaching the structure in an emergency. The PV array is on the ground, the disconnect is on the outside of the structure, and so is the AC disconnect. So very easily we can isolate all of this DC energy from the structure. In this drawing we have a multimodal PV system, and if they do have an energy storage system, it probably is a multimodal. Whether it's selling power back to the utility or not, it's probably a grid connected system with energy storage for backup. In this case it's in the basement. We have the batteries and the battery inverter, and everything's in the basement. The PV array is on the ground outside, which is pretty typical of systems with energy storage. So if this is the case, all you have to do is find that disconnect and you've stopped the DC power from coming in from the PV array. So the high voltage DC power is stopped at the DC disconnect. Number 2, that disconnect, that disconnects the interactive AC power from that inverter. Number 3 hopefully is outside, but it may not be. It may be inside in the basement. That would be the AC disconnect that shuts down the backup panel, the critical loads panel, this standalone AC panel. So that may or may not be outside. If it's outside, you've got all the AC power turned off, and then if you shut down number 1, you have the DC power shut down, except for the battery bank, which still has 50 volts and potential power in that. So if you know where that is, then you can just kind of be mindful of that potential in the basement. Here is a similar scenario. We have another multimodal system, but here we have, instead of in the basement, we have the batteries and the inverter, the battery inverter located in the garage. So your critical loads panel is in the garage, for standalone, and all of the equipment is too. Now that would be easier to identify. You probably have more visibility, more access. It would really depend on where the emergency was in the structure. And hopefully you would have all your disconnects outside. The DC, since this is a ground, that's your most important. The AC just shuts down any power usage or any AC power being produced. Here again, the critical loads panel, a standalone panel, disconnect may be inside. Here we have another multimodal system. Now bear in mind, these multimodal systems could be standalone systems. It would be just without the number 2 blue conduits that we see there. So it would be the same just without those. In this case, we actually have the PV array mounted on the roof. Could be the front or the back. And we have a DC disconnect on the back side of the building, and then the DC coming through. That number 1 disconnect on the back of the house may not be there. It may be inside the garage, or it could be inside the basement. So it just has to be readily accessible, as we said before. So here again, hopefully there's plenty of labeling, plaques, adequate plaques indicating where everything is, so you know where those DC conductors are running, because that's the only potential in there that's serious. The batteries are a potential. They're not as critical. They're not as high voltage. The likelihood of flooding them and shorting them out is not extreme. But that high voltage conduit, you want to make sure that you're not, cutting into it or creating another fire hazard by breaking it or something. Commercial systems are usually easier to work on. If there is an emergency on the structure, it's more likely that it's not located, very proximate to the PV array. It could be something's happening directly below the PV array and then penetrating up to the PV array, or it could be that the accident or incident happened on top of the roof and is coming down through, but the access is much better. In this case, we have a commercial flat roof with the PV array on top, and we have the inverter, which would be a central inverter most likely, on the lower level outside of the building. So this would be ideal. You can shut everything down, you can see where the conduits are running. The AC panel is probably located just inside the structure and the electrical room. In this case, this would be a later day, more modern, last few years PV system on a roof, where the inverters, I'm showing one inverter, but this would be probably multiple inverters on a roof, are located close to the PV array. So simply by disconnecting the power, you disconnect all the power up to the PV array. So just taking the meter out or disconnecting the main would do this. Chances of getting to an AC disconnect on the outside for the PV array is probably pretty slim. It's probably inside of the electrical room. Wind damage can create a hazardous situation on a roof. This is a commercial installation, both of these pictures are, and the modules are tossed about. Some of them are broken, and that means that there's a good possibility that the DC power is shorted to the frame of the module, which means everything metal that's connected to this PV array potentially is energized. So that's the big caution if you're working on a system that has damaged PV modules on top of a roof, is there could be live power up there. So take caution. Wear insulated, gloves, insulated boots, everything, and you probably can operate around this without too much of a hazard. Shutting down the whole PV system won't make any difference. If it's a string inverter system, there's high voltage everywhere. In these two photos, we're looking at a residential and a commercial fire that actually occurred in the PV array itself. This could have been internal inside of a module, or it could have been on a conduit that shorted or faulted somehow. In both of these situations, the PV array was the cause of the fire. Often, if it's on the exterior of the structure, it can be seen and put out ahead of time. Now, there is a potential. If these are microinverters, the potential is minor. You can just turn off the AC power and you're down. If it's a string inverter, an older string inverter with high voltage, then there is a little bit of potential up there. So if you're hosing it down, there could be electricity at that location, so just be mindful of that. This is not a common occurrence, but it has happened. The potential is there. The newer systems are safer, less likely for this to occur. Older systems had a little bit of an element of risk involved in it, so this did happen occasionally. In this photo, we're looking at a fire that occurred not because of the PV array, but the PV array was directly, involved in the collapse. It was right on top of the fire. In this case, you have another potential. If these were high voltage strings, then you could actually have a high voltage potential while this fire was going on. So that's what we're trying to avoid or find out about. If it's microinverters, not a big deal, nothing to worry about. If it's PV optimizers that are voltage safe, not a problem. If it's the old string inverters, or if it's a battery system with charge controllers, then the voltage could be somewhere between 80 to 500 volts. And so that's something to be very cautious of as you approach. High voltage conduit below the surface of the roof. So what's the likelihood that you'd run into that? 2012 after, probably very unlikely, because microinverters were used and then PV optimizers with the solar edge were used. Pre-2012, it's a possibility that there's a high voltage string running below the surface. If you don't see that conduit running off the side of the roof, then it runs below. And most of the time it drops straight down to the ceiling joist. Occasionally they'll run horizontally along the rafters. So there's a possibility. If you're above the PV array, it's unlikely that it's there. It's probably along with the PV array or lower if there is DC conduit with high voltage conductors in it. Covering the modules with an opaque tarp will reduce the voltage to zero, so it makes it safe on the DC side. I wouldn't do this until after the incident had occurred. The tarp could be a hazard itself. So this is usually done by a crew that's removing the PV array after something has happened and they're having to work on it. So this is a good maintenance procedure, but not an emergency procedure. Of course, it's unnecessary if you're using microinverters or solar edge optimizers. Well, let's review some hazards. Roof-mounted PV arrays pose two serious issues for first responders. One is access. We hope that there will be 3 foot on the margins of the eaves of the roof and on the ridge, but there's not necessarily. It's not a requirement in any state except California at this time. High voltage, especially high DC voltage, can create quite a hazard for starting a fire, a secondary fire, or shock hazard. If we have rapid shutdown mechanisms, which would be PV optimized solar edge inverters or microinverters, then we really don't have an issue. If it's prior to that, let's say 2012 and earlier basically, then we may have a high voltage issue. So we have to look for that conduit that feeds from the PV array down to where the inverter is. PV systems with energy storage pose two additional serious issues. Where is the AC and DC disconnect? On standalone systems, they will have a plaque more than likely, and the AC disconnect will be on the outside of the structure. Not guaranteed to be out there, but more than likely it will have a plaque identifying the fact that there is a standalone system in place. Multimodal systems have the same requirement, but they may not have the plaque outside, so that's something to be cautious about. The battery bank itself has a great potential of energy in it. If it were to short out and melt down, it can create a secondary fire. So most of the time we're in pretty good shape on this because the terminals are far enough above the floor. Even if there was some flooding, it would not reach the terminals to short it out. And then the only other condition is if debris fell on the battery bank, and usually the battery bank's terminals are covered or the battery bank itself is in an enclosure. So typically that's the case. So we want to look for the DC and AC disconnects. If they're not on the outside of the structure, we want to look at the two most obvious locations, which is the basement or the garage. Clearly labeled disconnects and directories make it much easier to work safely in the presence of a solar-sourced electrical generator, a PV system. Unfortunately, a lot of systems are not properly labeled. So what is the likelihood that you will see a labeled disconnect or a plaque on the exterior of the structure? If it is the main inverter AC disconnect, 100%. The utility requires that you cannot connect up an interactive inverter without it. The DC disconnect. Now, if it's a low voltage microinverter system or a PV optimized solar edge, then you're in the 100% zone. But if it's a high voltage PV array that doesn't have the voltage safe optimizer, if it's a ground mounted system, probably 95% of the time that DC disconnect will be accessible on the exterior. It may be higher than that. But if it's a roof mounted and it's one of the older inverters that has the high voltage, then probably 50% of the time. The other 50% is going to be inside somewhere. The rapid shutdown disconnect. Well, this is a new requirement, after 2015, where they require this on high voltage inverters. So before that time, probably 25% of the time the disconnect was actually outside and within 10 feet of the PV array. Probably less than that. So there is a potential for the old string inverter with high voltage and no disconnect within sight. There is a possibility of that. Plaque or disconnect for a standalone AC output. Multimodal systems, honestly, probably less than 25% are actually on the outside of the structure. Standalone systems, more than 50%. I would say it'd be closer to 100%, but it kind of depends on whether it's a cabin or whether it's an actual home as to whether it would have that. Procedurally, our process is to disconnect the AC power, disconnect the DC power. In the process of doing that, look for the DC disconnect label and labeled operating voltage. Identify the DC conduit route. Look for a rapid shutdown disconnect. Look for labeling that indicates that there's microinverters or the solar edge PV optimized. Disconnect standalone AC and DC. So if you can identify that there is a standalone system or multimodal system in place, look for that directory. If not, look in the garage or the basement.